So today we are going to discuss the concept of sampling error, which is one of the fundamental concepts in statistics. So in a routine practice, what we do is that we use the sample for the representation of population. And we had discussed in previous lectures in detail that what is meant by a sample. So when we have a larger population and we are unable to take observations for our desired variable from every member of the population, especially in the field research, then what we do is that we randomly take observations from different members of the population, and those members from which we have taken the observations, they collectively constitute the sample. And we say that this sample is actually the representative of population. So the statistic that we calculate from the sample, that should give us an estimate of the population statistic, right? So if sample is the representation of population, then the statistic that we are calculating from the sample, that should give us an estimate of the population statistic. For example, if we are calculating the mean value of some variable from the sample, then that mean value, that should give us an estimate of the population mean. Because we cannot have the absolute value of population mean. It is not possible to calculate the absolute value of the population mean. Why? Because we were unable to take observations from every member of the population, right? So therefore we took observations only from a sample, and because sample is the representative of population, so therefore the sample mean should give us an estimate of the population mean, right? So this is what is generally done with the larger populations. So usually when we go for sampling, the larger samples, if we collect the larger samples, they are going to give us a better estimate of the population mean as compared to smaller samples, right? And this is quite obvious, because if you have a large population and you're going into the field, and let's suppose you have taken observations from 15 individuals. The population is very large and you have taken observations from 15 individuals. And as compared to a researcher who has taken observations from the same variable, from the same population, from 150 individuals, right? So the second person has included 10 times more members into the data as compared to the first person, right? So which one is going to give us a more reliable estimate? The second one, because the sample size is larger and because more members have been included into the sample. So therefore, that is going to give us a reliable estimate as compared to the second one, which is smaller, right? So this is a general concept. This is a general rule that if you have a larger sample size, that is going to give you a more reliable estimate of the population mean as compared to the smaller sample. And we can understand this concept further by taking several smaller samples from the same population and then taking their mean values, right? So if we have taken several smaller samples from the same population, and when we calculate their mean values, we get to know that their mean values tend to differ from each other. So when we take several small samples from the same population, they generally provide us different values of the same statistic, for example, the mean value. Now, why is that so? That why they are providing us with a different value of mean? This is because variation between these individual estimates is because of the sampling error, right? So this variation between the mean values, because when we are taking several smaller samples from the population and they are giving us different mean values, so where this variation comes from? So this variation comes from the sampling error. So this variation in the sample means is because of the sampling error. Now, what is sampling error? Okay, so sampling error, right? So sampling error is responsible for giving us variations between the mean values of the samples which are taken from the same population. So sampling error is not a mistake of the observer, because as this term indicates that the error word is included into this. So this error is basically not a mistake of the observer, rather it happens by chance, right? So sampling error is an inherent characteristic. It is an inherent attribute of the sampling procedure. So it is inherently present in the sampling procedure, and it's not at all the mistake of the observer. It happens by chance. And why it happens by chance? Because some individuals have more than a fair chance of being sampled as compared to the other individuals. For example, if you're collecting individuals for taking the measurement for their weight, and you're collecting individuals, or you're catching those individuals with the help of a trap, and that trap has food as their bait, right? So obviously those individuals who are hungry, they will be more attracted towards that trap as compared to the individuals which are not hungry, right? So therefore there will be a certain type of the population members which will be attracted more towards the trap as compared to the others. And similarly, if you're catching the individuals, if you're catching the mammals, or if you're catching the birds, so those individuals, those members which are quick, which are swift, so it will be difficult to catch them as compared to the ones which are lazy, right? So this is something which is inherently present into the sampling procedure. So this is not at all the mistake of the observer, and it happens by chance, because some individuals, they have more than a fair chance of being sampled as compared to others. Now we understand these concepts with the help of an example. So we are talking about the sampling error. That first we discussed that if you have a larger sample, that gives us a better estimate, a more reliable estimate of the population statistic as compared to the smaller samples. And then we discussed that if we take several smaller samples from the same population for the same variable, then they usually give us different mean values. And why is that so? That why do they give us a different mean value? Because it is because of the sampling error, right? And sampling error is not something which is the mistake of the observer, which is the mistake of the researcher. Rather, it happens by chance, because some individuals, they have more than a fair chance of being sampled. So here we have taken an example, and in this example we have taken 10 smaller samples from the same population for the same variable, and you can see that each of these samples has got 10 observations, right? So we have 10 samples, and these have 10 observations each, and now we are going to calculate the mean values for each of these samples, right? From sample 1 to sample 10, we are going to calculate their mean values. So here we have the mean values for these samples, and here you can see that the first sample gives us the value of 74.4. The second sample also gives us the value of 74.4. The third sample gives us the value of 73.6. The fourth sample gives us the value of 74.7, then 73.4, 74.4, 72.7, 74.5, 74.4, 73.5. So you can see that each of these samples, that is giving us a different value. So there are some values which are exactly similar, and there are values which are closer to each other. But the thing is that there is a variation in these sample means, right? So variation in these sample means is because of the sampling error, right? So here we have these sample means. So what we are going to do now is we are going to see their distribution, right? The distribution of these means. So for that purpose, we can see that the sample means, they range from 72.7 millimeters to 74.7 millimeters. So the lowest mean is 72.7, and the highest mean value calculated from those smaller samples is 74.7 millimeters. So this is the range in which the sample means lie. And if we draw their frequency distribution, we can see that there are two samples that gave the mean value in the limits of 72.5 to 73.5. And there were 6 samples that gave the value in the limits of 73.5 to 74.5. And there were 2 samples that gave the value in the limits of 74.5 to 75.5, right? So this is the frequency distribution of these mean values, and we can see that this frequency distribution follows a normal curve, right? So this is a normal distribution. So what we have done is that we have taken 10 smaller samples for the same variable from the same population. And then we calculated the mean values for those individual samples, and then we drew the frequency distribution table for those mean values. And here we can see that these mean values, they follow a normal distribution pattern. Now, this observation that the mean values of the samples, they follow a normal distribution. So this concept basically is based on a fundamental principle in statistics, which is known as the central limit theorem, right? And it states that means of a large number of samples drawn randomly from the same population are normally distributed, and the mean of means is the mean of the population, right? So here, what we are talking about is we are talking about the mean of means, right? Which we can say as the grand mean, right? So if we take several smaller samples from the same population for the same variable, then we get different mean values, we get a variation in the mean values, and this variation, this frequency distribution usually follows a normal distribution, and the mean of means, which is the grand mean, that if we take the mean of all these mean values, so that is usually the mean of the population. So this is the concept, and this is the central limit theorem, and the grand mean or the population mean or the mean of means, it has its own standard deviation, which is known as standard deviation of means, right? Now, standard deviation concept, what is standard deviation concept? We had discussed in the previous lectures that standard deviation is the deviation of individual observations from the mean value. So here, what we are talking about is that we have the mean values, we have several mean values of the smaller samples, and then we have taken a grand mean value, and that grand mean value has its own standard deviation, which means the deviation of individual mean values from the mean of means, from the grand mean value. And the specific term for this deviation is the standard error of the mean, right? Standard or error of the mean, or simply the standard error. So what is standard error? Standard error is basically the deviation of sample mean from the population mean, right? Deviation of sample means from the population mean is known as the standard error of the mean, or simply the standard error. So what is standard error? Standard error is the deviation of sample means from the population mean, right? Because the sample mean is not the absolute or the exact value of the population mean, and the sample mean is basically used for the estimation of the population mean, but we know that the sample mean deviates from the population mean. So is there any way that we calculate this deviation? So yes, we can calculate this deviation by calculating the standard error, right? So sampling error, that can be calculated by the standard error, and this is the formula for standard error calculation. So this is standard deviation divided by the square root of the number of observations, right? So for calculating the standard error, we need to know the standard deviation and we need to know the number of observations, right? And why we are calculating the standard error? We are calculating the standard error because we want to know that how much the sample mean deviates from the population mean or the grand mean. And we are going to take the example of the shoot length. So here we have the frequency table for the shoot length distribution, and here you can see that we have 100 observations, and the lowest observation is 68 and the highest observation is 80, and then we have their frequencies mentioned here, right? So this is the frequency distribution for the shoot length. The mean value for this example is 74 millimeters. The standard deviation is 2.34, and the total number of observations are 100, right? So we have the mean value 74, we have the standard deviation 2.34, and we have the number of observations, which are 100, right? So now we are ready to calculate the standard error by dividing the 2.34 by the square root of 100, and we get the value, which is 0.234 millimeters. So standard error is 0.234 millimeters for this example, right? So how we are going to state the result in this case is the mean shoot length of the sample is 74 millimeters, and the standard error of the mean is plus minus 0.234 millimeters, right? So this is how we calculate the standard error. So we have calculated the sample mean, and the sample mean is 74 millimeters. And from this sample mean, we want to estimate the population mean. And for that purpose, we need to know that how much it deviates from the population mean. So this deviation is 0.234 millimeters. And this is how we can calculate standard error for calculating the population mean. Now the confidence interval, right? So as we discussed that we are taking sample, and sample is giving us the mean value, the sample mean value, and there is an inherent chance of a standard error that this sample mean value differs from the population mean, because every member of the population has got a different chance of being sampled. So therefore there is possibility of a standard error, right? There is possibility of a sampling error, and this sampling error can be calculated by calculating the standard error, and then standard error that gives us the deviation of the mean value, the sample mean value, from the grand mean or from the population mean, following the central limit theorem concept, right? So how we are going to get the population mean in turn, right? So we have calculated the sample mean, and we have calculated the standard error of the mean, that how much it deviates from the population mean. Now we need to know the value of the population mean. So the population mean, we cannot define this population mean in the form of a single number, in the form of a single value. Rather, we are going to define an interval in which the population mean is expected to lie. And this estimated interval of the population mean is known as the confidence interval, right? So what is confidence interval? Confidence interval is basically an interval, or it's basically a limit or a range of values in which the population mean is expected to lie. Because we don't have the exact value of the population mean, we can only estimate population mean, because our sample mean deviates from the population mean, and we have calculated that deviation as well as a form of standard error. So now we can give the confidence interval in which our population mean is expected to lie. And this is the formula for calculation of confidence interval, because as we discussed that the sample mean deviates from the population mean plus minus standard error, right? So this is how we calculate the confidence interval, the mean value plus minus z multiplied by SE, which is standard error. So what is this z-score? So this z-score basically defines us our confidence level, so that if we take z-score as 1, then our confidence level is 68%. And if we want to increase the confidence level, because 68% is not a good confidence level, it's not a good significance level, so therefore we need to take a higher level of confidence, and the minimum acceptable level is 95%, right? So people do it at 90% as well, but 95% is that confidence level which is generally agreed upon, right? So 95% confidence interval is usually taken, and for that purpose we need to multiply the standard error value with the z value of 1.96. And if we want to further increase our confidence level to 99%, then we need to multiply the standard error value by the z-score of 2.58, right? So when we do that, we are 68% confident that population mean lies within plus minus 1 standard error of a sample mean, right? That we have taken a sample mean, and we are 68% confident that our population mean lies within an interval which is plus and minus plus and minus standard error of the sample mean, right? And when we take the confidence level of 95%, we are 95% confident that population mean lies within plus minus 1.96 of the standard error of a sample mean. And when we take the 99% confidence interval, we can say that our confidence level is 99% and we are 99% confident that population mean lies within plus minus 2.58 standard error of a sample mean, right? So this is our confidence interval. That confidence interval is basically an interval. It is basically a limit in which our population mean is expected to lie. And what is the central point in that range? The central point is the sample mean. And because the sample mean deviates from the population mean, so we calculate that deviation as standard error. And when we use the standard error as such, right, that when we take the z-score as 1, we are only 68% confident that our population mean is expected to lie plus minus of standard error of the sample mean, right? And if we want to increase, then we have to increase the z-score as well. And if we take the z-score of 1.96 standard error, then we are 95% confident that the population mean lies within plus minus 1.96 standard error of the sample mean. So we are extending our interval, right? And if we want to further increase our confidence level, we need to further extend it by the value of plus minus 2.58 of standard error of a population mean, right? And we are going to see that. So you don't have to worry that where do we get these values of 1, 1.96 and 2.58. So we are going to see in the next slides that where do these values come from. All right, so to understand the concept of the z-values, that where do we get these z-values, we need to understand the properties of the normal curve. And here you can see that we have drawn a normal curve, a normal frequency curve with a normal distribution. And we have standard deviation scaled onto this normal curve. So in the center of the curve, you can see that we have taken the population mean. So population mean is in the center of this normal curve. And then on each sides of the population mean, you can see that we have scaled the standard deviation, right? So this is the standard deviation of the mean values from the population mean, right? It's the standard deviation of the observations, the standard deviation of the values from the mean values, that how much they deviate from the mean value. So this is the normal curve, that in the center we have the population means, and then arrows on both sides. You can see that these arrows, they basically demonstrate the deviation from the mean value, right? That how much are the values below the population mean and how much are the values above the population mean. So these arrows on both sides, they represent these deviations from the mean value, right? So, but what do we have? We have the normal curve drawn over here, and in the center of the normal curve, we have the population mean, and then on both sides of the population mean, we can see that how the values, they deviate from the population mean, right? And we have scaled that deviation as -1 plus 1, as -2 plus 2, and -3 plus 3. So this is the magnitude of deviation on both sides of the population mean. So this is the normal curve that we have. Now let's suppose if the area under a normal curve is 100%, right? The area which is bounded by the normal curve, the area which is bounded by this blue curve, right? This blue colored curve. So if that area is 100%, right? If we say that this area is in total 100%, then the area bounded by one standard deviation on each side of the central axis is 68.26, or approximately 68% of total area, right? So if the total area under the curve is 100%, then 68% of the area, it is bounded on -1 plus 1 of the central axis, right? So our central axis is our population mean, and if we go 1 unit down and 1 unit up, so this area is going to be 68%. So this is going to cover 68% area of this normal curve, right? So if the total area of the curve is 100%, then 68% of the area, it is bounded by -1 plus 1 standard deviation around the central axis. Now, how do we interpret this thing? We interpret this thing is that if we are randomly taking any observation from that population, then there is a 68% chance that that observation is going to lie within -1 plus 1 standard deviation of the central axis, right? So 68% of the observation randomly drawn from population will fall within plus minus standard deviation from the mean value, right? So in the center, we have the mean value, and if we go to measure their standard deviation, then standard deviation -1 plus 1 on both sides, so that is going to cover 68.26% of the area, right? So it means that 68% of the observations, they are lying within this interval, right? So this is the concept of interval. So we have an interval, we have the central point, and then we have an interval of -1 and plus 1, right? And what is the confidence level of this interval? The confidence level of this interval is 68%, right? And if we want to increase our confidence level, we will have to increase our interval size. And for that purpose, we need to include 95% of the area under the curve, right? So when we take -1 and plus 1, we are covering 68% of the area of the normal curve. And if we want to increase our confidence level, and if we want to include 95% of the total area, then we will have to go minus and plus 1.96, because minus and plus 1 is 68% of the area, and minus and plus 1.96 is going to give us 95% of the area. So here we have our second interval, which is 95% confidence interval, which means that 95% of the observations randomly drawn from the population are expected to lie within this interval. So they're going to give us observations that are going to lie within this interval. In other words, we can say that if we are going into the population and we are randomly picking up one observation, we are randomly taking one observation from that population, there is a 95% chance that that observation is going to lie within this range, right? So this is the confidence interval of 95%, which is plus minus 1.96 of the central axis, which is of standard deviation on both sides. And if we want to further expand our interval, if we want to further increase the confidence interval, and we need to include 99% of the area, right? That we require that our confidence interval that should have that should cover 99% of the area. Then for that purpose, we need to expand our limits to 2.58 plus minus 2.58, right? So if we draw our limit to plus minus 2.58 of the central axis, then this is going to cover 99% area of the curve, right? So that is going to give us even a better estimate, right? The 99% confident estimate of the population mean, which means that a randomly drawn observation from the population will fall within this interval, and we are 99% confident in this interval, right? The 99% observations of this population are going to lie within this interval, and if you are randomly picking up one observation, there is a 99% chance that that observation is going to lie within this interval, right? So this is the concept of the confidence interval, and this is how we take these z values, right? So these z values, they basically describe the area of the normal curve, which is under a specific interval. So when we take the z-value of 1 minus 1 plus 1, it means that it is covering 68% of the area. And when we take the z-value of minus and plus 1.96, it is covering 95% of the area. And when we are taking the z-value of 2.58 plus minus, that is covering 99% of the area. So this is how we get the z-scores or the z-values. So now that we have understood the concept of the z-values, that what is meant by the z-value, and how do we use these z-values in the calculation of confidence interval. So now it is time to calculate the confidence interval, and the formula for confidence interval is this: the mean value plus minus z multiplied by standard error. So when we calculate the 68% confidence level, we take the z-value of 1, and when we take the 95% confidence interval, we take the z-value 1.96, and when we take the 99% confidence interval, we take the z-value of 2.58, right? And we are taking the same example that we were studying, that we had 100 observations of the shoot length from a population, and their mean value was 74. And the standard error that we calculated for that example was 0.234 millimeters, right? So we have put in these values into our formula for the calculation of confidence interval, and now we are going to see that what is the result that we get, right? So we are 68% confident that population mean lies between 73.766 millimeters and 74.234 millimeters. And how did we calculate this one is that we put in the values 74 plus minus 1 plus minus 1 in 2.234. So we are going to add and subtract this value 0.234 from the mean value of 74. So first of all, 74 minus 0.234, so that gives us the value of 73.766, which is the lower limit of our 68% confidence interval, right? And when we add this value into the mean value, that's 74 plus 0.234, so that is going to give us the upper limit of this 68% confidence interval, which is 74.234, right? And then we calculate the 95% confidence interval, and for that purpose what we do is that again we use the same formula, that we multiply the 0.234 value of standard error with the z-score of 1.96, which is for the 95% confidence interval, and we get the value of 0.459. And then we are to add and subtract these value of 0.459 from the mean value. So when we subtract this value, we get the value of 73.541, which is the lower limit of this confidence interval. And when we add this value, we get the value of 74.459, which is the upper limit of this confidence interval. And then we calculate the 99% confidence interval, and for that purpose we use the z-value of 2.58. So when we multiply standard error with the z-value of 2.58, we get the value of 0.604, and we add and subtract this value from the mean value, and we get the value of 73.396, which is the lower limit of this confidence interval, and we get the value of 74.604, which is the upper limit of this confidence interval, right? So this is how we do the calculation for confidence interval, by using the z-score and the standard error, and then we take their product, and then we add and subtract that product from the mean value, right? Now we are going to see that how we can state the results of confidence interval, right? So we can state the results as the mean shoot length is 74 millimeters, and then in the bracket we are going to write the confidence interval, which is 68% confidence interval. We need to mention that what level of significance, what level of confidence we are talking about, right? So 68% confidence interval is equal to 73.766 to 74.234 millimeters, right? And then we state the result for 95% confidence interval. So the mean shoot length is 74 millimeters, bracket start, 95% confidence interval equals 74.541 to 74.459 millimeters, bracket closed, right? And then we can state it for the 99% confidence interval, that the mean shoot length is 74 millimeters and the 99% confidence interval is 73.396 to 74.604 millimeters, right? So this is how we are going to state the results for the confidence interval. Now I'm going to repeat this again, that what is confidence interval? Confidence interval is that interval in which our population mean is expected to lie. And this is not going to be a single value, rather this is going to be an interval. This is going to be a limit in which our population mean is expected to lie. And how much is the confidence, how much is the estimate level? The estimate level is 68%, 98%, 95% and 99%, right? So generally we choose 95% confidence interval as the minimum confidence level, right? So how do we calculate this confidence interval? For the calculation of confidence interval, we need the value of standard error, and we need the value of the z, and we need the value of mean, right? So when we use these values, we calculate the confidence interval, right? And what is the concept of the standard error? Standard error basically calculates us the sampling error, right? So it gives us the sampling error, or it gives us the variation between the sample means and the population mean, or when we take several means from the same population, then that variation is explained by the sampling error, and we can correct that sampling error, or we can calculate that sampling error by calculation of the standard error, which is basically the deviation of mean values from the grand mean value, which is usually the population mean, if we follow the central limit theorem, right? So once we calculate the standard error, we need to calculate the confidence interval, and if we use the standard error as such, if you multiply standard error with the value of 1, we are only 68% confident. But if we want to increase the confidence level, we will have to increase the expand of our standard error, and we will expand our standard error by 1.96 on both sides to get the 95% confidence interval. And then we will expand our confidence interval, our standard error by 2.58 on both sides to get the 99% confidence interval, right? So this is how we calculate, or this is how we estimate population mean from the sample mean. So this is the whole philosophy. Now let's consider that we have a smaller sample size, right? So in the previous example, we were talking about the normal curve and a larger sample, because the larger samples, they have usually a normal frequency curve. So the distribution of observations in the normal curve is usually normally distributed. But if we have a smaller sample, then as we discussed, that the smaller samples, they give us a less reliable estimate of the population mean, because they don't have a normal distribution, right? So if we have a small sample size, we cannot have a large number of observations for our sample. Then what we do, that how we are going to calculate the confidence interval for the population mean. So in that case, instead of the z-score, we are going to apply a correction factor, which is taken from the t-distribution table, right? So z-score is applicable when you have the normal distribution and when you have a larger sample size. But if you have a smaller sample size, then you are going to use the t-value, because in the smaller sample size, it is likely that your sample is not going to have a normal distribution. So therefore, you're going to use the t-value. So the confidence interval formula in that case is going to be confidence interval is equal to mean value plus minus t multiplied by standard error. So this is going to be the formula of confidence interval when you're using the t-value. So instead of z, we have the t-value. And this value of t is taken from the t-distribution table using degree of freedom and desired level of confidence. And we are going to take the example to understand that how we are going to take the t-value. So example is the masses of mammals. So we have 10 observations here, right? So we have 10 observations, and the number of observations is smaller in this case, which is 10, right? So we have total 10 number of observations, and when we calculate their mean value turns out to be 21.42. Now, from this mean value, we want to estimate the population mean of that population, right? That we are talking about the masses of a mammal, right? And then we have calculated the sample mean, and we want to estimate the population mean of the mammals for the variable mass, right? The standard deviation is 1.84, right? And what we need to calculate next is the standard error, right? Because for the confidence interval, we need standard error. And for standard error, we need the value of standard deviation and the number of observations, right? So we calculate the standard error for this data, which turns out to be 0.5825, right? So now we have the mean value and we have the standard error value, and then now we need to see that what is the t-value. So for the t-value, we need to have two categories, or the two factors that we need to consider. The first one is the degree of freedom and the other one is desired level of confidence. And as we know that desired level of confidence is usually starting from 95%, so we will start from 95%. And the degree of freedom, so remember, what is degree of freedom? Degree of freedom is n minus 1. The total number of observations minus 1. So in this case, degree of freedom is going to be 9. So now we see the t-distribution table, right? So in the t-distribution table, you can see that the values, these are two-dimensional, right? So each value within this table, each cell within this table, so it corresponds to two factors. One is the p-value and the other one is the degree of freedom, df, right? And in the bottom you can see that the z-values are also mentioned and the confidence level is also mentioned. So what is our desired level of confidence? Our desired level of confidence is 95%. And what is the degree of freedom in this case? It is 9. So we are going to take the observations from two-tailed p-values. We are going to discuss in the next lecture what is meant by two-tailed test and what is meant by one-tailed test. So for now, you are going to take the p-values for the two tails. The desired level of confidence is 95%, which is the probability of 0.05. And the degree of freedom in this case is 9, right? So now we have to figure out the value which corresponds to 9 degree of freedom and probability of 0.05. So here we have this value. So this value 2.262 is the value which lies on the degree of freedom 9 and probability value of 0.05, right? So this is our tabled value of t. So this is the value of t, this is the score of t that we are going to take from the t-distribution table. And what do we need to get this score? We need to know our desired level of confidence and we need to know our degree of freedom. And now we are going to select the next value for the 99% confidence interval, again for the two-tailed p-value, and the 99% confidence interval is at the probability of 0.01, right? So the degree of freedom in this case is 9. So the value that we are going to get for t at probability of 0.01 and degree of freedom 9 is 3.250, right? So this is the value of t at degree of freedom 9 and probability of 0.01, which is our significance or confidence level of 99%. So now we have all the desired inputs ready for the confidence interval calculation. So we have the mean value, which is 21.42, and we have the t-value, and we have the standard error value. So our first level of confidence is 95%. So the t-value that we took from the t-distribution table was 2.262, and the standard error that we calculated for those 10 observations was 0.5825. So what we are going to do is we are going to multiply 0.5825 with 2.262, and then we are going to add and subtract the outcome with the mean value. And for the 99% confidence interval, we are going to do the same. We are going to multiply the t-value, which is 3.25, which we have taken from the t-distribution table, and we are going to multiply this one with the standard error, which is 0.5825, and then we are going to take their product and add and subtract that from the mean value like we did previously. So our result is that the mean mass of mammals is 21.42 grams, and the 95% confidence interval is 20.1 to 22.7 grams. And the result for the 99% confidence interval is that the mean mass of mammals is 21.42 grams, and 99% confidence interval is 19.53 to 23.31. So here we have defined the confidence interval. So I'm going to repeat all of this, that what is sample? Sample is that group of individuals that belong to a population from which we have taken the observations, because it was not possible to take observations from every member of the population. So therefore, the observations were taken from randomly from different members of the population. And those members from which we took the observations, they collectively constituted the sample, right? And sample is the representative of population. Therefore, the statistic that we calculate from the sample is actually the estimate of population statistic. It is not the absolute value, rather it is an estimate of the population value. And for example, we have collected mean value of some variable from the sample, and we want to estimate the mean value of population for the same variable. So in that case, what we are going to do is that we are going to calculate the sample mean value, and then we want to have an estimate of the population mean. And when we are going to estimate the population mean, we cannot have a single value. We cannot have an absolute value of the population mean. So therefore, we are going to calculate an interval in which the population mean is likely, or it is expected to lie. And that interval in which the population mean is expected to lie is known as the confidence interval, right? So confidence interval is basically that interval or that limit in which the population mean is estimated or expected to lie. And how do we calculate this confidence interval? We calculate this confidence interval by taking the mean value of sample and then using the standard error value to calculate that interval, right? And the because we are talking about the confidence interval, so we need to define our confidence level as well, that how much confident we are in stating that interval. So the minimum acceptable level is 95%, which is generally used all over the world in different research fields. Then 95% is the minimum acceptable confidence level, right? So 95% confidence interval is calculated from the mean value and from the standard error, and then the 99% confidence interval is calculated from the mean value and the standard error. And what does this interval mean? This interval means that our population mean is expected to lie within this interval. So when we go into the population and we take a random observation, there is a 95% chance that that observation is going to lie within this range. For example, we took the example of these mammals, that we took their mass observations, the observations for their masses, and then we took their mean, and then we estimated the confidence interval, and we calculated the confidence interval, 95% confidence interval, as 20.1 to 22.7. So this is an interval of observations, and we can say that if we are going into this population and we are going to randomly pick up any observation from that population, that observation is likely to lie within this range. So there is 95% chance that that observation is going to lie within this range, right? So this is what is meant by confidence interval.